Okay, Chris. Yeah, but okay, okay. Look at this one. ठीक है जन्म झाला I'm alone. Yeah. Thank you, Krishnan. I'm at Hanle present now. I'll show you the observatory from outside right now. It's a little bit busy, so I.
Okay. 1 minute.
Right now.
Yeah.
Okay. You
Yeah.
can see the observatory at city at Io Hanle. Okay. So this is the observatory right now. I'm on the western side of Hanle at the top of the mountain. We have some estimated going with the wind. We have a GPS station, carrier station for carbon.
Namya, you are not visible, sir. You can see it in the gallery mode. It is there. Yeah, yeah, I did pin. We request participants to bear with us. It is
Yeah,
a remote place
yeah,
from we are
yeah.
doing
It's
this live
connected.
stream. Yeah,
Yeah, yeah.
yeah, yeah.
So this is the satellite link for connecting with crest of Postcoche, and we have some restrooms and a control room for the internet link, and this is the Kaufman
Recording in
Mountains
progress.
across the. Okay, it's windy and cold outside.
So there is a audio issue. I mean, low bandwidth. So it's nothing but he's first going out of the observatory dome, and from outside he's showing, and now he's entering into the telescope.
Okay, now we are going at the yeah. Right now we are going at the telescope floor. So we will just in a moment. The telescope is around 15 meters at height from the ground. So we are just reaching the telescope. That's the dome of it. So
Yes, there is. This will be their internet issue. Just bear with us. Namgyal, your video is not visible. It always happen. Unfortunately, rehearsal always will be good, and when the final thing comes, it went on. Sorry about that. Okay. Namgyal, you are there? Yeah, okay.
Hi, hello.
Yeah, you make your video on. Yeah, back. In between, you went off for
Hello, Christian. Yeah, can you get me?
you went off for a few minutes. Uh, yeah, you can go ahead now.
Yeah, yeah. Right now. Yeah, yeah. Now we will open the dome shutter. Okay.
So here the telescope is kept
So
under the dome, and this is the one
yeah.
opening slit. Now they are opening the slit.
So
Yeah, you can
this
continue.
is
Yeah.
yeah. So this is the Altimeter Telescope, and it was installed in first side of the telescope was in September 2000. September 2000 onwards. So it's like 25 years back.
Namgyal, your audio, can you increase a bit near to microphone?
Functioning without any problem technology. So this is the most D2 telescope in India right now. It has a very low launch period.
Namgyal, audio, can you nearby the microphone?
At the back of the telescope, and we have very clear sight in Hanle actually. We have around 225 neither spectroscopy around 180 or 190 objects. Totally corporation.
So this is about
So
the
we will
back
go
end instrument he's talking about now. Namgyal, your audio is not sound enough.
so,
But we trained like this. Okay.
yes, fire.
Yeah, okay. It's about the CCD. Prasanna, if you want to talk about anything, you can go ahead.
Yeah. So I just help them because the audio is not clear. So what he's showing is the main telescope, which is kind of
charged
used for
capabilities.
observing
Yes.
stars. Yeah. And then the camera, blue color objects which you're seeing in the bottom are the instruments. So basically, there is a camera which is useful for taking the images. And as you can see, the structure is metallic, but the top portion is made up of truss, which is pipe, basically tube structures. And on top, in those tubes, there is a secondary mirror, which is reflecting the light back to the instrument. So the middle horizontal portion, which is indicated by white, is having mirror. So he will show the zoomed in version. Yeah. So the blue is the instruments. Yeah. You can see it is rotating as well.
Yeah.
So because telescope is alt-azimuth mount, when the observations are happening, the image plane rotates on the cameras. So to compensate for that, we'll have mechanisms which will help in correcting the plane, as well as when there are limited side ports. So what happens is when we want to change a camera or type of instrument we are using, we have to rotate this port so as to bring the desired instrument in the line. So along with this camera, there is a room below this telescope where there is a big high resolution spectrograph as well. Yeah. So the light is taken from here via a fiber
Now I'm talking
to
with
the
you.
instruments.
It's not audible for you. Prasanna, is it possible to communicate about Namgyal? Okay, you continue. Anyway, your voice is...
Yeah, actually, voice is very less from their side. But so that's what I was saying, that we use telescope for collecting light, and it is analyzed by using cameras and spectrographs. So what you were seeing with the blue color instrument was an camera, whereas there are additional instruments like spectrograph below the observatory. And now you can see the telescope is rotating. So this is basically alt-azimuth mount where both the axis, horizontal and vertical axis, can rotate. and you can point this telescope to a given star. So, and the black color kind of cover which you're seeing in the middle is nothing but the basically spider for covering the mirror for avoiding dust to settle in the daytime. But in the observing time, it will open. Yeah, and then the mirror will be exposed to the stars. Yeah, so now you see that cover is opening, and the shiny part in the middle region is 2.2 meter, basically 2 meter primary mirror of the telescope. Yeah, so a telescope is defined by its characteristics in terms of its primary mirror size, and then the focal length, and so on and so forth. So one of the major factor is the diameter of the telescope, which decides the resolution. And here, what you're seeing is one of the India's biggest optical infrared telescope, which is Himalayan Chandra telescope. Yeah, so what he's showing is the secondary mirror. So from primary mirror, lights gets reflected and gets focused, or rather converged towards the secondary, and from there it comes back and goes into that black color cylinder which you're seeing in the middle, and there is a hole to the primary mirror, and then light goes behind the primary mirror to the instruments. Yeah. That is the mechanism. And you can see behind this telescope there is a white color slit open. So that is the opening from where the telescope looks outside, or rather outside light comes inside on the telescope. So we have a shutter on top of the dome which opens in the night time. Now they are not opening too much because it will flood the light because of the daytime. Yeah.
Maybe last 10 minutes we will give you by 2:20. We can give an interactive question and answer session. Maybe we can.
We'll try to answer most of your questions towards the end. And as you can see, they're rotating the telescope. So conventionally, telescopes used to be of equatorial mount, where the axis of one of the axis of telescope will be aligned to the pole star. Whereas this is a modern day telescope which is on alt-azimuth mount, and this particular helps to point object by using two axes, point towards the star object. What he's showing is a HROS camera. Yeah.
This is the clear strip of infra is to observation and this is in collaboration with Mumbai.
Yeah, so what he was showing is the infrared camera which is built in collaboration with TIFR. It's quite difficult to work in that environment as well, and we should appreciate all our engineers and operators over there who have to work in a very cold temperature. What he's showing is to make things even cooler. So that tank, what you're seeing is a liquid nitrogen tank, and then they will fill that liquid nitrogen in the diwar of CCD. So cameras used here are cooled down to negative minus 270 or so as to make them work at even cooler temperatures than the outside environment, and this helps in reducing the noise in the cameras. Yeah, so things are to be made so as to work in a cooler temperatures here.
So right now the telescope is the
telescope is now, you can see it is pointing towards the zenith direction. Zenith is basically when you stand and look up, that is the zenith direction.
Is our person.
And you can also see some yellow color wires and blue color wires in the bottom. So those are basically the cables going to the cameras, motors, and so on and so forth. So they need to be managed properly. Hence, telescope cannot rotate in multiple rounds. So it will make a 360 turn and come back again to its original position. So, yeah.
Hey, Prasanna.
Yes, yes.
I have one doubt. That is
Yes.
Celestron attached.
Yes, yes. So there is an additional telescope attached on this telescope, and that is used for basically guiding the telescope as well as it can be used as a seeing monitor. Yeah. So
that's nice.
That is additional.
Once upon a time, we used the normal thing. Now Celestron is inclusive.
Yeah. Previously, there used to be a customized small telescopes used to help in guiding and pointing this telescope. Whereas because the field of view of main telescope will be very small, so it becomes difficult to point big telescope directly to a given target. So this helps in.
We have some computers here, which is first one is the masterpiece is collector data and the tokens.
Now he's talking about the control room, which is at the bottom.
So the control room is in relatively cozy place, just below the main floor, but it's still cold and people have to work in extreme environment. And from here they will control the telescope and as well as collect the data and store it safely. I think we have lost the connection to them, but yeah, I was saying like now they're back. We will pin them.
One more thing, in case if you want to be very lively experience without internet, then VBO also we are placing on by Sunday 6:30 plus. You can join that in that also. Of course, wherever we go, we are always taking the hill station where out of the city and all the facilities, the internet connection there also will be there. But
hello, Krishna.
Yeah, yes.
Yeah.
Hello.
Yes, Namgyal, you are audible. You are audible. So can you move on to growth? We are already 220.
Yeah, so actually they were showing us the control rooms from where they can do different operations for observation as well as for storing the data and communicating this data to the astronomers who are sitting in Bangalore. So there is a remote link from
He's
Bangalore
trying to ask, Prasanna, he's trying to ask something.
Yeah.
Yes, Namgyal. Tell me. Yeah, tell me. Namgyal, you are there. We can switch over to. Yeah, we can switch over to growth. I'll WhatsApp them. Yeah, Prasanna, you continue.
Yeah, so I was saying like for observing, typically astronomers used to go to the telescope and do the control from there itself. But nowadays, due to the remote link via satellite, astronomers observe this telescope from Bangalore campus, where there is a CREST facility, from where we have a dedicated satellite link for this observatory. And in the beginning, Namgyal shown us one dish antenna which was located outside this observatory. So that is helpful for establishing this communication link because it's very remote from the city and internet connection is.
We can switch over. We can switch over to growth.
Hello.
Yes, Namgyal, you are audible. We can switch over to growth. Hello.
Yes. So now we are planning to switch to growth telescope, which is another telescope on the same site. So it is half-meter optical telescope used for doing remote observations or rather robotic observations of transient events and so on. Yeah.
Actually, the growth is situated something remote again, but we are trying to satisfy you with different people connecting on the thing, so that may delay. Sorry for that.
No, but Crispin, another person is going to be from
Yeah,
growth, right?
Yeah. I have a video. Maybe will it satisfy if I play that gap?
Yeah, I mean, because we have limited time, so maybe you can proceed with the video.
Okay. Just tell me whether my sharing mode is on.
So there is one question. By the time you're sharing, there is a question about how many telescopes are there. So on this summit, we called it as Mount Saraswati. There are two big telescopes. One is Himalayan Chandra telescope at City, and then there is a Growth telescope, that is the robotic telescope of 0.5 meter. And then there are small site survey instruments also on top of this mountain. But at the bottom of this mountain, there are two telescopes. One is Haga telescope, which is a gamma ray observatory, as well as it is a kind of combination of 6 mirror telescopes. It acts in an array. And then there is another one called as Maze telescope. Let's see this video first. This is the HCT, main 2 meter telescope, which you just now seen. The instruments and telescope can rotate.
Tell me, Ramya.
This is a high resolution spectrograph which is located below the mirror, below the telescope.
No. What about growth? No, nothing is audible. Audible was very poor. Anyway, we engaged with Rasana talking about all those things. But what about growth? Are you showing now or it is over?
You can see there are several. And this is a newly installed telescope called as Maze.
No, it's not visible. Check.
That was segmented mirror telescope.
1 minute.
Combined with coming from stars.
Yeah, so, I couldn't see any other video other than now to fill the gap. I am sharing the video.
Less population and less resources, but thanks to our engineers and operators from Hanle who are doing fantastic job of keeping this telescope
please do it so fast.
Hello.
Yes.
Growth connect with the global. Growth connect to global.
Yeah, people are there at growth, but there was something.
I think there is a connection issue. So let's by the time they're establishing the connection, we can talk about some of the questions which are coming.
Hello.
You didn't get the control. Growth is working. Yeah. You didn't get the control to sell.
So who is controlling from growth?
Because I have assigned as a co-host. Now try. No, but anyway, now anyone can share. Tell me the name. Okay, 1 minute.
Yes, people were asking about the TMT session, so it will start after this particular session.
1 minute.
All the questions.
Yeah. Norla also, right? Norla also. 1 minute.
Yeah, somebody's mentioning that.
I'm oftenly giving because of.
Seeing the optical telescope for
this
the
is
first
the
time.
Growth India telescope.
Yeah, they are on.
Just got the control. Yeah.
Yeah.
So this is a Growth India telescope, and 0.7 meter mirror.
Yeah, we can cut.
We have a 4K by 4K CCD there indoor. We have SGSS UGRIZ filters, and here is the small azimuth focuser and derotator. This is the mirror. Inside is the mirror. So mirror अच्छा है हमारा. 0.7 meter. Field of view is quite large, which is 0.7. It is especially for transient events. So that's why wide field of view. So opening the mirror shutter here. So the telescope is randomly pointing to some direction.
So this telescope has a high sleeving speed, like 15 degree per second. It can go up to 15 degree per second of sleeving rate, which is useful for observing non-sidereal objects, like the moving objects, near Earth objects and transient objects. So the camera's resolution is 4K by 4K, and the pixel scale is 0.6 arc second. And here is the filter wheel unit with the SDSS UGRIZ filters. So here is the dome, which slaves with according to the position of the telescope.
Yeah, no, everything is perfect.
Yeah.
Audio and everything. Okay.
Yeah. So already. Yeah. So that's it from growth.
Okay. Okay. So what about next?
That secondary mirror is covered because it's sunlight right now. So that secondary mirror there. Let me show you. So next, over to Norla from MES. Over to
Yeah. So
yeah,
Norla,
so I'm stopping the video now.
Yes, yes. Norla, you there? I had to assign. He's co-host only. And he can share. Norla, you there? Oh, Norla, audio was an issue, I think. Okay, if audio is the issue, you
let me show you the view from the dome itself.
Yeah,
so it
thank
seems
you.
he's not able to connect.
Yeah.
All right. So that there is the Hanle monastery. You can see that's a monastery there, and at the base camp we have our gamma ray telescopes, the MACE and Hagar, and also we have a small 50 centimeter optical telescope also there. So this is the landscape view from inside the dome of growth. The sky has been poor for a few days, so it seems today we are getting a clear sky. It's quite windy. So that there is the weather station. As you can see, there we have a weather station, and there at top you can see an instrument that's a dim seeing monitor. So that is the site for NLOT, future bigger telescopes. So we have a seeing monitor instrument there. All right. So that is our rest rooms and the kitchens at top.
So you can also say that practical difficulty from there to here internet connectivity goes. So we are switching over to different people. Yeah.
Yeah. So that's it. Yeah, that's the HCT right there from growth dome. So we have a mirror coating plant also there. So that is the mirror coating plant, and behind that we have solar panels. So we have 60 kilowatts of solar powered power here. So the power at the observatory is coming using solar panels, like solar power, and that's it.
Yeah, thank you, Stanton.
Mm-hmm.
So okay, I think
so. Yeah, I think that's all from Hanle.
Okay, so we are.
So at best camp, it seems we have an internet connection issue. So sorry for that. So this mountain is called Dikpa in Ladakh and Mount Saraswati. So this mountain shape is in a shape of a scorpion. If you see from top, this will look like a scorpio, you know. That's why it's called a Dikpa mountain. Yeah. So I'm texting it, so like the telescope is on placed on like above 30-40 meters above the ground for like clearers and seeing and all those things. No? So here is the control room of growth. So we have a this is the control room of Growth India Telescope. So the telescope operation is automated. It means it runs through scheduler mode. The scholars from IIT Bombay and IIA, they give schedules every night.
Okay. Anyway, I muted.
So this observatory, like it is located on a very nice location. Like so, we have plains on the boundaries, and we have very smaller mountains on
It
the
is on
side by. So it is on a high peak. The obstruction of mountains.
You do one thing. You log in this. Ask Neeraj to get the link and log in and project, na? Just to get an overall view. Yeah, thank you, Stan. It is nice.
So yeah, should I stop now?
Yeah. Okay. So yeah.
So I can show you more of outside, but it's very cold today, so you can see my hands totally red. Yeah.
Yeah. Thank you. Then.
Thank you, everyone. Yeah. Thank you.
Okay, so hope we could satisfy people. Sorry for this internet, but it is the practical situation. It's not that we cannot solve it because such a remote place and hardly everything is arranged. And but for observation purpose, that is a separate thing. So that will be without any issue with the thing. Only to make it to connecting with the internet and making you people with the Zoom, that was the difficulty. Okay, then we can move on to the next session, TMT. So, Neeraj. And I'm very happy that we are packed with the limitation, 100 participation limitation. Still, we are 95. Yeah, thank you then. So, for the next event, this is the same link. We are continuing. So, TMT. And whoever wants to continue with the next event, you can be here, and you can let others to in. If you are happy with that, you can be here. But if you are using, you can continue it. Okay, so that others, whoever wants to follow that, they can follow it. And if the number is packed again, we will send the YouTube link also. Make it open. Yeah. Okay then. Yeah. So, Neeraj, who is Rasana? You can start. Right? You there?
Yes, Crispin, we are ready.
Yeah. Tell me Ramya ID. Only the Ramya, right?
Yeah.
Okay.
Yeah, me and Ramya.
Okay. I think I assigned the correct co-host. Yeah. Ramya, you there? Can you speak? Ramya? Hello?
Hi, Crispin. Can you hear me clearly?
Yes. Fine. Okay, so the floor is on you. You can carry on. Is there anyone moderating? Okay, fine.
So, Neeraj, can we start off, or are we waiting for some more time?
No, you can start.
Okay. Thank you, Crispin. So, hello all. Welcome to this session. This session will be on the 30-meter telescope. This is going to be an interactive session with one of the engineers who is closely working with the 30-meter telescope. So I am Dr. Ramya Sethura. I am project scientist working at India TMT Coordination Center at Indian Institute of Astrophysics. And
more light gathering power, the sensitivity of telescope increases. And in this case, in comparison to world's biggest telescope as of now, which is Keck, we are going to have roughly 80 times more sensitivity. So that's the reason why we are building such a large telescope, so as to do a kind of observations of deeper and fainter objects in the universe.
That's quite something. So, isn't India a partner in building the 30-meter telescope? So, which are the other countries which are participating, and what is the nature of our participation? Could you just reveal something about that?
Yeah, so that's quite interesting because building a telescope of such a large size is not easy because of two reasons. One is the technology required for such a telescope, the capacity required for manufacturing the components, and as well as the amount of money we had to spend on building such a telescope. So for such a large projects, which cost billions of dollars, single country cannot do it. So hence, multiple countries like India, China, Japan, US, and Canada, we have come together so as to build one single large telescope, and it will be 30 meters in diameter. Now, when we say we are partnered in this telescope, we are having 10% partnership, which means we will contribute 10%. And it doesn't mean that we're going to give 10% of the money required for building this telescope, but rather we are going to have a very different kind of contribution, and that is called as in-kind contribution. So in this mode of operation, what we do is majority of the kind of spendings which we'll do will be in kind, which means we will fabricate the components required for this telescope here in India, and then we will send it to project. So it will help in two sense. One is we will meaningfully contribute to the project and we'll get to use this telescope. But at the same time, our Indian industries and research institutes will get exposure for building such a large telescope, which will be eventually helpful for building our own telescopes here in India as well. So there is a quite a good contribution. So if I had to say more in detail about what is that we are giving to this telescope, so around 84. Yeah, so around 84 mirrors will be fabricated here in India, and these mirrors are not manufactured using conventional technology, but it requires something called a stressed mirror polishing, because as I mentioned in the beginning, that this telescope shape, the primary mirror shape, is a hyperbola, and each of the mirror segments should fit in that hyperbola. And hence, as you know, that unlike a sphere, each portion on the hyperbola is having different conic constants. So hence, we have to manufacture this mirror by stressing the mirrors initially, polishing them to a sphere, and then releasing the stress. Then this mirror deforms, and then it will be part of that hyperbola. So such kind of advanced technology is required for polishing these mirrors. And presently, there is a new facility which is built here in Bangalore, which is part of IAA, and it is called as ITOF. And in this facility, these mirrors will be fabricated in coming time. So presently, this facility is under commission. But this is one of the contribution. We also contribute a lot of mechanical components. This is one example wherein we are giving something called a segment support assembly. Now, when you have a mirror segment, which is made up of glass, and the support structure, which is made up of metal, when you put them together, you can't stick them together like two papers or two wooden planks. Here, you have to support them flexibly. The reason for that is as temperature in this metal expands differently than the glass which is used here. So we are using one specialized glass called as clear serum ZHS, and that is having very, very low thermal coefficient of expansion. So which means when temperature of the around the observatory or inside the observatory changes, the metal structure will expand, but the mirror will remain there itself, and it will not have any added stress developed because of such a complicated but necessary mechanism. We call it as segment support assembly. So, and it also helps in basically giving a soft support to the mirror, because it is as good as supporting this mirror on our fingertips. So when our base of rather our hand is having different expansion, the top of the mirror will remain there because metal structure is going in the horizontal direction. So that is kind of a mechanism. And it also has a very unique feature of correcting any deformations on the mirror segment itself. So when we manufacture this mirror, we are expecting that the surface of the mirror should be as close to that hyperbola, which I mentioned. But it's not always possible to get ideal shapes or exact shapes. So what we do is any residual errors which are remaining on this mirror are corrected by exerting additional forces below this mirror at 27 locations by using additional small motors which you see here. These are the actuators specially designed for this application. So this is the way we can bend and correct each of the mirror segment so as to make each segment part of that hyperbola. But this telescope is in extreme environment again, as you've seen just now, our Hanle Observatory. Similarly, our plant site is in Hawaii, wherein temperature can change a lot. And then these telescopes will be experiencing wind, vibration, all sorts of disturbances. So mirror segments may deviate from each other as compared to that ideal hyperbola. So for correcting mirror position within that hyperbola, individual mirror segment, we use bigger actuators, which are called as soft actuators, which are also contribution from India, and they will help in kind of bringing back the entire mirror segment within that main profile by giving tip, tilt, and piston. These are the 3 degrees of freedom of a plane. So by doing that, we can bring this mirrors back to the main hyperbola, and we are manufacturing around 1500 such actuators. And but that is about correction. But how do we know that a given mirror segment has deviated from its original position or expected position? That is done by using edge sensors. So these are the gold coated glass blocks, and they act as a capacitive edge sensors, and they are quite accurate, like better than 5 nanometer accuracy, and they will be able to detect any relative shift of a given segment from other neighboring segments, and by measuring these sensor values, we command those bigger actuators.
You said gold coated, Prasanna?
Yes. So we are having this here. We are having a gold coated sensor because one, gold is it doesn't corrode over time, and this telescope is going to be used for 50 years of its life. So yeah, by the time I didn't mention that the lifetime of this telescope is designed as a 50 years. So each and every mechanism and component going in this telescope should be heavily tested and validated so as to have reliability of 50 years of life. So, and there are so many thousands and thousands of components are involved in here. So we had to ensure that when we manufacture, say, 3000 edge sensor pairs or 1500 actuators, not many of them, of course, some of them may fail, and we had to do a regular preventive maintenance, but we don't expect that many of them keep failing every given time. So we have to make them as reliable as possible. And we, of course, we have a math behind it, how reliable, when we say out of 3000 sensors, how many sensors can fail, so as to make it manageable.
So, Prasanna, primary mirror forms the heart of the telescope.
Correct.
And so these are the 3 important components which will keep the telescope in shape. So one is the actuator, the support assembly you talked about, and then the final edge sensors. So, and all these 3 are being supplied by India to TMT.
Yes, this is a very strategic, I can say, contribution for this telescope, because they form a part of the main mirror, which is primary mirror. And so far, as I said, the last big telescope which was built in here in India was Venugopal Observatory, which was 2.34 meter. And after that, there are not many big telescopes which are fabricated here in India due to the lack of technology which is required for building such a telescope. And now, due to this contribution which we are doing to the telescope, to the 30-meter telescope, we are gaining that know-how and technological understanding of how to build the primary mirrors for such a large telescope. Because looking forward, our needs are going to grow. Indian astronomers are going to require larger telescopes, and to build a 10-meter class telescope, which is one of the favorite kind of topic in these days, we are going to require these technologies. And hence, as you can see, all the contributions which you are doing are around the primary mirror of this telescope. So it's quite a useful contribution in 2 ways. One, we get to use this TMT, but also we get to use the technology for ourselves. Yes.
And you also have a software component here, which I see
Yes.
on the
So we are also contributing software. When we think of India, and as you know that like software is a major kind of driver in Indian economy. So almost entire software contribution required for this telescope is going from India. So this particular flowchart shows uh, all the different softwares required for entire TMT, and the red color blocks which you see here are contributed from Indian side. So it's a majority of chunk of software is going from our side. Yes.
That's true. That's quite a significant participation India is providing to TMT. Yeah. Prasanna, can you also say, like there are many questions in the chat also. Everyone wants to know when and where will this telescope be built?
Okay, this is a very interesting question, and we are also waiting for this telescope to complete. So this is a large telescope, and it requires a lot of efforts in terms of developing technologies, validating them, making them as reliable as possible, and then kind of realizing or fabricating the final components and then putting it in the observatory. So presently we are in final design phase. Most of the subsystems, some subsystems have already past this final design phase and they are in production round. Whereas presently we are prototyping the final designs of these actuators so as to confirm that whatever designs we have are the ones which will go in the observatory. So that we are expecting around 2024 to 25 that all the design reviews will be completed and the actual site construction at the site, which is Mauna Kea mountain in Hawaii. That is our preferred site as of now. So that is expected to start around 2025. And once we start that in phased wise manner, we will start growing the size of this telescope as component arrives. We'll start putting them together, validate them. And it will take roughly 2034 to 35 to have this telescope fully operational with the first generation instruments on it. Yeah, so it's quite kind of challenging task, and that's why it takes some time.
Yeah, Prasanna, you show here India TMT Coordination Center, which is in IIA Bangalore. So are there anybody else contributing to this telescope within India?
Yes. So India TMT Coordination Center is kind of a nodal agency which is participating in this project and contributing to the project from Indian side. And it is constituted by three premier research institutes in India. One of that is IIA Bangalore, from where we are conducting this program. And then there is another institute called Ayuka from Pune, and then another institute which is ERIS from Nainital. So these are three institutes who constitute this India TMT Coordination Center with its headquarters in IIA Bangalore. And there are other research institutes as well as a lot of industries are also partner in this telescope. They're contributing quite significantly, and it is kind of a joint collaborative effort. And it is fully funded by Department of Science and Technology and Department of Atomic Energy. So yeah, that is how we kind of constitute ourselves. And yeah, so this is the site which before the question which you asked, so where we are going to have this telescope. So this is our preferred site, Mauna Kea, which is around 4,000 meters above the sea level. This is a volcanic mountain in the middle of Pacific Ocean where you have extremely good seeing conditions for astronomy, for doing observations of astronomical nature. And then already there are telescopes. You can see all these small white dots. These are the telescopes which are already present, and this is the graphical representation of TMT on this side. And yeah, so we are hoping that this construction starts soon and we'll be able to use this telescope from there. Yeah. So, of course, this telescope is also meant for doing a lot of science and a lot of interesting science, rather. So, I just want to first turn the table and ask Ramya, because she's involved into a lot of science related activities as well as instrument building related activities for this telescope. So, Ramya, can maybe let us know that what TMT can see and what are its main science goals.
Prasanna. So India TMT is involved in the science instrument building also, that we are building a wide field optical spectrograph, and we are contributing for heavily for high resolution optical spectrograph. So these instruments will be looking very farther and very fainter objects. So there are many science cases which TMT will be able to observe, basically many objects. The dynamic range is quite huge. What do I mean by that is, as you can see in this picture, I will talk about three science cases which the TMT will mainly focus on and make significant contribution in the field of astronomy. One is to study the first stars and galaxies. So the first stars and galaxies after Big Bang, there were only nothing at all. Then there was Big Bang, where space and time was created. We know the story. Then there were only kind of quarks and all the uh, uh, basic quantum physics acting there. And then suddenly there was something called as the cosmic dark ages. During this cosmic dark ages, there was no light at all. But somehow, at some point of time, the hydrogen collapsed to form huge, massive stars, mass 200 times or more massive than the sun. And these stars started exploding and ionizing the whole universe. So that is what we call as the first stars, and the galaxies immediately followed. So, and we are currently at the redshift of 0, and the first stars are believed to be formed at redshift of 10 or 12, which is about hundreds of gigaparsecs away. So this is how far it can go, that it can study the nearest our solar system objects, and also it can study the first stars and galaxies which were created just after a few hundred million years after the Big Bang. So that is one of the most important science cases which TMT will be able to understand. And that is basically because of the TMT's resolution. You already mentioned it is 10 times better than HST and also 5 times better than JWST. So you can see on the right here how good the resolution of TMT is. The middle figure shows how the HST will look at this galaxy, but then with TMT you can see much more features of the center of galaxies. So that is how good the resolution will be to study these objects. So the second science case which we will be focusing on will be the galactic center. That is where this year's Nobel Prize also came. 2021 Nobel Prize. Andrea Gas was one of the persons who got the Nobel Prize. This is because she used a tedious set of observations, because it's a 10-year observation, to understand how the stars move around our galactic center. So when it comes closer to the galactic center, the stars speed up. So this is because of a huge mass present at the center of the galaxy, and that huge mass is nothing but the presence of a massive black hole at our galactic center. So of course, adaptive optics is very important for this. She had used Keck telescope for doing these observations, and you can see the number of stars is much more at the galactic center when compared to what she could really observe, or her team could really observe. So with TMT, we will be able to increase the number of stars, and the confusion between the stars will not be there with the TMT, or will reduce with the TMT. That will help us to understand the galactic center. So not only our galactic center, but it will also be helpful to understand supermassive black holes of other galaxies, which is present in other galaxies as well. So then the third important aspect which the TMT will be able to significantly contribute is in the field of exoplanets and its atmospheres. Till today, there are about 5,000 exoplanets, that is extrasolar planets which are not belonging to our solar system, but external planets. So there are already about 5,000 of them, which is being detected by Kepler mission and the TESS mission together. They are the candidates. So that is detected using the Doppler Doppler measurements and also using transit spectroscopy. But with TMT, we'll be able to directly image these extrasolar planets, as you can see on the right here, where the central star is totally blocked. And what you see on the other 3 dots are the planets for this particular solar system. So TMT will be able to confirm all of most of these candidates. Apart from that, we'll be able to also study the atmospheres of these planets. So so always the bigger question is whether we are alone in the universe or whether there is some alien life existing. So the biomarkers or the bio signatures which these atmospheres could have, if there is a life, is like carbon monoxide, oxygen, and methane are the 3 biosignatures which we will be looking at by doing very high resolution, high sensitive spectroscopy of this planets. So there will be quite a significant contribution from TMT. And mind you, this will be on habitable zone. So TMT will be able to take spectra of exoplanets present in the habitable zone where we expect life to exist. So that will be a very important contribution from TMT.
That's really fantastic because it covers many different diverse astronomical topics. And Ramya, one more thing which I wanted to ask you about the multi-messenger astronomy, which is these days a very trending topic. And what is multi-messenger astronomy and how TMT fits in this domain?
Can you go to the next slide, please? So in this picture, we try to see how the universe has begun and has reached to the current state. So in this currently TMT, as I mentioned to you, will reach as far as the first stars and galaxies. There are other mega science projects which are aimed at identifying or understanding other aspects of the universe, like the LIGO or the square kilometer array in the radio wave band, and INO in the higher wave bands or higher energies. So we'll be able to understand about a system or about a galaxy or about an object in all these wave bands. So we'll get a complete picture of what is happening in that particular object. So this will be each of these mega science projects will be complementary to each other and will be giving us more information about the objects which we are interested in.
So that's fantastic. So there are like so many this large scale mega science projects, and whereas we already have so many optical infrared telescopes here in India, we just witnessed 2 of them in the previous session. So once TMT is commissioned, will this telescope be obsolete?
No, Prasanna. So I would like to think it in this way. Before the advent of 10-meter class telescope, or let me put it this way, 2 to 4-meter class telescopes have been very useful in discovering new sets of objects. Be it even the amateur telescopes are very important. They have discovered several novae, supernovae, basically what we call as the transient objects in the sky. And then the larger telescopes, like the 10-meter class telescopes, have gone up and done the follow-up observations of those objects which were discovered by 2-meter class telescopes. So in this way, if we see 2 to 10 meter class telescopes will never be obsolete. That will provide the science cases for us to be able to observe or do a very detailed study in the TMT. So this 2 to 10 meter class telescopes will never be obsolete. Of course, we have to think of intelligent ways how to use them, maybe form a network as the growth is already contributing in the network of telescopes, or build very intelligent science instruments which will be very helpful in understanding the new transient phenomena, which keeps giving surprises every now and then for astronomers. So yeah, so we have to think about intelligent ways of using it, but it will never be obsolete.
That sounds good, Ramya. So yeah, as you can see, like these are the existing 10-meter class telescopes all over the world. Whereas as we seen in the beginning, one of the biggest telescopes in India is around 3.6 meters. So we are in once the TMT is ready and we have it available for use from for Indian astronomers. There is definitely a need of having larger telescope of this size, like of 10-meter size. So what next for India in the domain of 10-meter class telescope?
Yeah, as you rightly said, the one which we have now is a 3-meter or 4-meter class telescope, 3.6 meter at Devastal. And the next we are contributing to build is a 30-meter telescope. So there is a large gap here. That gap needs to be filled using the 10-meter telescopes. So within India, yes, we are planning for national large optical telescopes. Astronomers in India have carefully thought for the need of this national large optical telescopes, and they are currently in the concept phase to bring out a national large optical telescope. It is definitely required. For one, the 30-meter telescopes is very challenging to obtain time in the 30-meter telescope, because all of the world will be trying to observe through the 30-meter telescope. So it will be observing with the niche areas and providing discovery kind of sciences. But to fill this gap, we will need this 10-meter class telescope within India, so that our own astronomers will have a possibility of observing through the 10-meter class, and be able to provide science cases for the 30-meter telescopes. So other 10-meter telescopes existing in the world is not fully accessible for all the Indian astronomers. So there is definitely a need for 10-meter class telescopes within India.
Yeah, thanks, Ramya. And then, as we indicated in the beginning, that the components and the contribution which is happening for TMT, the same type of contribution or same technology can also be adopted for building such a large telescope. So, hence, our India's participation in TMT project is very strategic, and it is going to be helpful for realizing such a large 10-meter class telescopes in coming time. So,
yeah.
all right.
I think let us stop here, and
Yes.
shall we take questions? Niruj, you have your hand raised.
So before, I had a question about something maybe you could speak a bit more on. Considering all these really exciting telescopes which are going to come up in the future, we are right now at the stage where we are building them, right? So what are the opportunities for engineers in India and at IIA who want to get involved at the stage of building the telescopes?
Yes. So as I said, like India's contribution for specifically for this project is around manufacturing of these mirrors, for which we are having a new facility coming up here in Bangalore, which will require kind of a lot of people from optics background to be part of. Then we are also having mechanical components like SSA, segment support assembly, which requires mechanical engineers from our side to manage the work packages which are required to be fulfilled for TMT project, but as well as engineers who are interested in this field and the companies who are working with us. There are opportunities with them. So mechanical engineers, optical engineers, and there is a lot of electronics involved. So there is a scope for electronics engineer. Then optics and coating related aspects are also involved because optical mirrors require coating, as well as the sensors which we are using are having gold coated glass blocks. And you can see there is a patterning here. So this is done by using laser etching techniques. And then there is a instrument designing. So design engineers are required. Then there is a software. And so every now and then there will be some job postings which will be available on IAP as well as TMT's website, for which interested engineers can look for. And not only here in India, but all our partners as well as main TMT office also offers several job openings for engineers who are interested in contributing to this telescope project. So in addition to that, there will be some project related students also who come to IA and contribute from while they are in their MSc or in their BTech courses. So that kind of opportunities will also be there. Ramya, you want to add something more towards the science side of it?
Yeah, so there are scientists at in Indian Institute of Astrophysics and elsewhere also give or develop science cases for observing through TMT. So we will also require science background students who can come and contribute to understanding first the science cases and then be able to at least contribute in developing a few of the science cases by doing short-term projects. So the one thing is you will have to write to itcc at iiap.res.in. We will leave the address below, and the concerned person will be directed to the requirement. So yeah, please look into our websites and keep watching. If you are a BTech student, then you should be able to apply as an intern. And we have quite trained about more than 10 to 15 of them, right, Prasanna? So quite a large number of interns come every year for projects.
Rasana and Ramya, there is one interesting question from YouTube. Like Adil Desai, by the time the telescope is fully operational in 2025, won't the instrumentation and the other techniques become slightly obsolete and require newer stuff? I mean, we are in the updating all the things, right?
Yes. So this is also a very interesting question. As I said in the beginning, that we are building a telescope which needs to last for 50 years. So yeah, commissioning is like say 5 to 8 years from now or so. But the overall operation is going to be 50 years. So hence we have to think about whether we will have sufficient spares available, whether the technology will be capable of, or whether technology will be available at that time. So what happens is as we go ahead, the technology improves and newer hardware and software and other the processes come into market. So what we are doing as of now is the things which will be difficult to make at that point of time, we are making them in spare. So for example, when I shown you the main element of this telescope, which is its primary mirror. So this primary mirror is having 6 sectors. So there are 492 mirror segments altogether, and they are distributed in 6 similar sectors. So all the mirrors in this sector are identical with this, with this, with this, and this. Whereas while fabricating or while manufacturing, we are making 7 sectors. So we have one full sector as a spare available for several reasons. One is, suppose one of the mirror gets damaged later on, we'll have the exact replica of that mirror to be replaced. As well as the mirrors are coated with reflective material, and that needs to be recoated every 2 years, basically. And now you imagine there are 492 mirror segments. And if you keep coating one mirror in a day, roughly 492 days will be required to have all the mirrors coated once again after 2 years of its life. So almost every day, some or other mirrors are getting coated in the observatory facility. So that one extra spare sector will also be helpful as a spare when the mirrors which are removed from this telescope are getting coated. Again, here you can see 492 mirror segments are required. We are making 580. We need 2,772 edge sensor pairs, but we are making around 3,300 of them. We need 1,476 actuators, but we are making 1,500 plus 1,525 actuators or so. So yeah, so this way we are ensuring that we have sufficient spares for things which are difficult to make later on, but things like computers or network hardware or similar things which are growing in as time passes. So we are relying on the technology which will be available at that point of time. So hence we delay to purchase those hardwares or to build those hardwares till we are ready to start putting this together, telescope together, which is a few years activity. So at that point of time, we will get the hardware which is available in the market at that point of time. So one example is network switches, which are a lot of network switches, Ethernet switches are required across this telescope because this telescope is controlled via PoE, power over Ethernet switches. So yeah, so that is how we, even the computers, we are relying on the computers which will be available at that time. So maybe around 5 to 10 years from now, whatever computers will be available, we are considering their power to be utilized for this telescope. So that is just one example. Yeah, and then another very tedious task for being part in this telescope, but which is more rewarding, is the documentation. So each and every system which is built and used in this telescope gets documented very properly, so as to track back what was the configuration used. Suppose we are making an actuator, all the 50 parts which are going in there, we keep records of how they were made, what were the dimensions when they were made, what was the material used for this, whether they were certified or not. And then also we keep the track of which batch of material is used. For example, if you're using some aluminum material, we keep a log till it's manufacturing of that raw material in the industry. Suppose it is coming from some steel house. So from there till the fabrication and use, we keep the entire record and it is well documented. So documentation is also one way in which we can keep track of something goes wrong later on.
Okay. Saharsh Jain is having a question. Do you want to unmute yourself and ask?
I think they may not have a facility, so maybe we can repeat the question.
In the Zoom, Saharsh Jain.
What does he have? Yeah, he has asked here. Okay, he's saying like since UI UX designing is booming in India, as well as we have seen one of the biggest recruiter NASA in America to design the interface and satellite. So what is the scope of designers in this? So yeah, when I say designers, we were talking about designers of the mechanical, optical, electronic systems. So that kind of scope is there. But as you know that this telescope project is in place from last couple of years. India is partner from 2014, but the telescope is being conceptualized and designed from last 10 years or so. So majority of the designs are kind of frozen. We are just validating them. And now is the time where we are manufacturing, or we are going into production mode, where we will manufacture a lot of thousands of components. We will inspect them, we will document them, and we will assemble individual subsystems and send it to the project. So, yeah.
Pardon, Prasanna. Am I audible?
Yes, yes.
So my question was like in NASA, one of my known person worked in a project in the Hubble telescope, and that its replacement as well, the new telescope which is in the space right now.
JWST.
So they design, they their work was to effectively design that structure of the basic connection systems. So my question was, since ISRO and our space system is keep on developing throughout the years. So what will be the future in the Gaganyaan mission or these space laboratories, etc.?
Yeah. To be honest, presently it is in very initial phase in terms of Gaganyaan, and to be honest, we are not the right person to answer on Gaganyaan vision because we are more onto TMT. Whereas, I mean, all these projects are very much multidisciplinary projects, and there will be a need of all different fields. For example, building such a massive structure of TMT requires almost all the mechanical, all the engineering branches to be utilized to have a successful design. So right from CFD engineers, right from mechanical, civil, electronics, you name it, you will need those people to be used for or to be utilized for this kind of massive project. So there will be scope, and then there are a lot of parallel activities happening. As Ramya also mentioned, that TMT is one of the project, but there are so many mega science projects which requires immense amounts of engineering. There is an INO project which is Neutrino Observatory. Then CERN India is partner from quite long and contributing significantly in terms of hardware. Then there is a FAIR project. Then there is a SK project. This is also a very large square kilometer radio telescope project, and this is kind of India is also partner in this. Then TMT, as we discussed today, there is an ITER project for nuclear fusion related experiments, and then there is a LIGO project which is coming up in Maharashtra. So wherein there will be a gravitational wave detector which will be used. So in this also there are a lot of different diverse background people are required, right from optical, mechanical, electronics, civils. Then a lot of sensors are used in this LIGO project. So it is a multidisciplinary. The astronomy is now into kind of a multi-messenger and multidisciplinary phase where to build the telescopes, build the instruments, you need people from all the background. Yeah.
And I had one more question. Like, if someone had to join IIA as a bachelor, or I just want to get into this telescope line. So, what should be my procedure for that? Yeah.
Yeah.
Yeah. Okay, thank you.
Yeah, we will not answer that question so as to keep your excitement till that event on 28th.
Thank you. Thank you.
Yeah, someone is asking, please show all the slides. Actually, our intention was to show only these many slides. So the rest of the things are just backup. Yeah, someone is asking ITCC website. Maybe you can just Google search. You will get India TMT Coordination Center. You will get the first website.
We don't have anything else. I think we can close the session. Prasanna, thank you very much for patiently answering all the questions and giving us details about 30-meter telescope and India's contribution. I thank you for your time. Thank you, Crispin and Neeraj, for arranging this. Thank you.
Yeah, thank you, everyone. And I think there may be additional questions, so please feel free to write us on ITCC's website or ITCC's email ID. You will find it on Google. Thank you, everyone.
Sorry, sir, to disturb you in the middle, but I cannot chat. I had a question. Can I ask it quickly? I'm so sorry to disturb in the middle, but there was a thing about this two telescope, like you told in the Ladakh observatory, that with the other telescope, the main one, there was also an extra telescope. Could you explain more about like why we use that extra telescope? And I did not quite understand that working procedure.
Yeah, so basically, main telescope is putting light on the main camera, whereas the other telescopes are helpful to keeping the target star exactly in the middle. So if it deviates from the axis of the telescope, we bring it back and we know it by using this additional telescope. It is a viewfinder kind of thing.
Okay, thank you so much.
Yeah, yeah. Thank you, everyone. Have a good day.